All right, hello and welcome back, everybody. Today we're talking about a very interesting topic and probably one of my favorite topics in multivariable calculus, and this is that of potential functions. And really briefly, I want to talk about why are we calling these potentials. So, for example, the electric potential being voltage, for example, is an example of these functions. That's really where the name came from, was electric potential, or even other potential energy curves. So you can think about a ball being on top of a hill has very high potential energy. The hill itself represents a potential, where if the ball started to roll, then it would roll down what we would call the potential gradient. So that's where these names are coming from with potentials. And what they are, what a potential function is the equivalent to an antiderivative, but for vector fields. Okay, so the idea is, how could we take an antiderivative of a vector field in some sort of higher dimensional setting? And these are the potentials. So, I mean, jumping back to our idea with electric potentials, the electric field is the gradient of an electric potential. Okay, magnetic field, gradient of magnetic potential, etc. So we have this one-to-one relationship between fields and gradients, and then recall that the gradient was a derivative, but it's a vector derivative. It's a derivative, and so if it's the derivative of some potential, that potential is a scalar field, which then creates the field if you were to look at how the scalar field changes over space. And that's where our words electric field and electric potential come from. Or vice versa. That might be why we have the names potential functions here. Okay, so this is, like I was saying, we want to kind of think about this in the sense of antiderivative. So recall our fundamental theorem of calculus. We can either represent it as, the derivative of the integral is the function itself, or the integral of the derivative is the function itself. And we always have to be careful in the reverse direction, because we can always gain an extra constant out of that. So if we wanted to do something similar for where we're headed, right? We're headed towards getting rid of this gradient f, partial f, partial x, partial f, partial y, partial f, partial z. Somehow from this information, a vector, we want to recover, given that vector, recover f. So somehow from those three partial derivatives, we want to recover the original function f. So let's just look at one of these partial derivatives, partial f, partial x, and try to recover f from this. Well, it shouldn't seem that difficult that to recover f from a partial derivative with respect to x, we would take, say, find antiderivative only in x. Right, that's kind of our idea, is we would find an antiderivative only in the x variable, given my scalar field from the previous page, x plus yz. The gradient of f is 1 z y. Now let's pretend that I don't know what f is. So I'm going to completely get rid of f. And let's only look at the gradient. How could I recover f? Well, let's just try to undo the gradient in 3 steps. So let's do 3 steps. Step 1, undo partial f, partial x. Step 2, undo partial f, partial y. And step 3, undo partial f, partial z. If I work in these 3 steps to undo a partial derivative, I'm going to integrate the partial derivative with respect to that variable. And in this case, my partial derivative with respect to x was just 1. So if I integrate 1 dx, I recover x plus c. If I undo partial f, partial y, I must integrate with respect to y. And the partial derivative was z there. So z, taking a derivative with respect to y, I can kind of think about this. Z doesn't care about y doesn't care about z. This is really the integral of 1 with respect to y, and z just kind of sits along for the ride. This gives me zy plus c. And if I undo the derivative with respect to z, that's undoing the partial derivative with respect to z. I'm going to take an antiderivative dz and recover partial z was y. I recover y dz, and just like before, y is sticking along for the ride, and I get yz plus c. Okay, these three do not agree. Right, my three antiderivatives don't agree. And so that brings into question if the three antiderivatives don't agree, what was f? Well, if we recall from the beginning, I had said way back here, given f equals x plus yz, we can start to see some similarities here. There's x, and there's yz. So we find pieces of f in each case, but we don't find all of f in each case. We find pieces of f, but not all of f. Why? So there's exactly one reason why, and that's that, grab even one more color here, these two terms, this yz term, or this one up here, under partial x is 0. And so that's almost like how constants were disappearing. For regular derivatives, constants disappear under the derivative. Since yz is a constant with respect to x, it disappears. And so this c over here in x is really c of any function y and z. And the c in y is any function of x and z. And c in z is any function of y and x. And these c's are where we can start to figure out how to recover the real function. So then the question of all of these finding potentials, call that C1, call that C2, call that C3, is can we find a C1, which was a function of y and z, a C2, which was a function of x and z, and a C3, which was a function of x and y, so that all antiderivatives agree. This is what it means to find a potential function. We are searching for these, we're taking antiderivatives, notably, in each direction. But that's only going to give us parts of our potential function. The rest of the potential function has to arise from us finding these three constants which exist in the other variables for each of the potentials, so that all of the potentials are in fact the same function. And so we can see in this case, the C1 of yz, I compare to the other two cases and I say, okay, C1 of yz, how can I get that to agree with the other two cases? Well, I can make C1 equal to zy. And in C2 xz, how can I make that agree with the other two cases? Well, I can make it equal to x. And C3 yx, how could I make that agree with the other two cases? Well, this case is now zy plus x. This case is now x plus yz. These are the two same cases. This c of y and x just needs to be x. So that's what I'm noticing here, is that I'm going to replace C1 yz with yz. I'm going to replace C2 xz with x. I'm going to replace C3 yx with x. And now all of a sudden, we have actually recovered. They all agree. I have x plus yz, x plus yz, x plus yz. All three antiderivatives agree, and they happen to be my true potential function here. This is how we find antiderivatives of gradients. Okay, I know this was a lot of work. We can practice it a lot more in class, but these are a little bit of work, and that's okay. So let's go back here. And what the book is trying to say this more, I guess, in writing, but I think we've seen everything we need to for this. And there are some steps here in the book, which is basically what I've showed you on the whiteboard. But let's actually try one more example of this, because I know these are a little bit tricky. So let's see if we can find f. Can we find f from the gradient given on the left? Well, let's go ahead and integrate with respect. Let's integrate partial f partial x with respect to x. That's going to give me y plus z integrated against x, and I get yx plus zx plus, now keep in mind, this constant is going to be a function of y and z. If I integrate f with respect to y, x there, this is x plus z dy, and I recover xy plus zy plus a constant in x and z. And if I integrate with respect to z, I have x plus y dz, which is xz plus yz plus a constant in the variables x and y. And now if I compare all three, I see that I have a yx and a zx in the first one. I have an xy and a zy in the second one, and I have an xz and a yz in the third. So I need to find things to add in the other two variables in each case so that I make all three of these the same. And I'm starting to notice, okay, what is this piece missing that this piece has? And it's missing precisely zy. Okay, so I'm going to replace c1 with zy. Now I notice, what is this piece missing, which this piece has? And I notice that this piece has zx, so I'm going to replace cxz with zx. And finally, what is this piece missing, which the other two already have? And the other two already have either xy or yx, they're the same thing. And so I'm replacing c3 with xy. And thus my potential function has to be what I've come up with, which agrees on all of them, xy plus yz plus xz. And all of a sudden we found a potential function. Okay, let's scroll down and see if that's right. And there you go. But the astute among you might be noticing that everything's the same, and yet they've added a constant here. And that's still going to be true. We have to be careful, from what I've said before, is that potentials can always vary by a constant. This is why we had to make the definition back in the I think it was the late 1800s, that we're going to measure all heights of all mountains by sea level, right? Because mountains really are just potentials, and if we ask about the potential at the top of the mountain, we need to know what the zero is with respect to, and that's really fixing this C, because we could have gone up and down as deciding what our zero is. We could decide the center of the Earth is the zero, or the top of the Eiffel Tower is zero for some weird reason, or something like that. So potentials can in fact always vary by a constant, a true constant, but I never worry about it too much. I know some people can be very pedantic about these constants, but you don't have to worry about me being too pedantic about those. So there's something interesting here, and this section is called requirements for potentials, and I want to talk about why this section even exists. So this is a very important fact. Not all vector fields have potentials. Okay, that means that there are a lot of vector fields out there, probably the majority of vector fields out there, that don't arise from the gradient. Most vector fields don't arise from the gradient of a scalar field. And this is somewhat unfortunate. This is a very unfortunate aspect of multivariable calculus, is that we can't always take antiderivatives. We'd love to always be able to take the antiderivative of a vector field, but we can't actually do that. So here, this idea of requirements for potentials says, how can we tell, just looking at a vector field, whether or not we're able to find an antiderivative? So this is, given V, a vector field, is V equal to the gradient of f for some f? Very important question right there. Well, let's see. Something that's really important to note is that if v equals gradient of f, then we have this nice property that the curl of the gradient is 0. But this is true only if v is a gradient. So it turns out that the curl of any vector field which has a potential is 0. How can I think about this heuristically? Well, potentials correspond to the gradients of something like a hill. So if a ball is going to roll down a hill, the ball's not going to gain angular momentum out of nowhere, right? Conservation of angular momentum says that if the ball started with 0 angular momentum, it needs to end with 0 angular momentum. And that's how we know that the ball is not going to all of a sudden be given some sort of angular momentum rolling down a hill. And that's really the way that we can think about potential functions. It's all of the vector fields which impart no angular momentum on the particles which flow through them, or something like that. Okay, and that's the same statement here, right? So because the curl of the gradient is 0, then the potential is going to always be curl-free. And these are actually if and only if statements, right? Every curl-free vector field will have a potential, and every gradient of a potential will be a curl-free vector field. Now, proving that the above statement is true is one of your exercises. Yeah, so and then this is really interesting, right? Because this comes from one of Maxwell's equations. Right? If we look at the curl of the electric field, we know that has to be 0. So that's really nice. That's really nice. That's why a lot of these are very important. So let's look at a few of these other properties. There's something nice about vector fields which arise from potentials, and that's that we give them a very special name. We give them the name conservative. And this is what I was saying earlier. Conservation of angular momentum is exactly what we're talking about here, and other conserved quantities. Is that these vector fields, you can find a lot of quantities from the vector fields which are conserved. And in some sort of vector field that's not going to arise from a potential, then you lose a lot of these conservation laws. So mathematically, what do these conservations look like? It looks like the following. It says that, now this is a lot of math notation for saying one thing. It says that paths through, so integration of paths through conservative vector fields only care about endpoints. So in some sense that means no matter what path I take or a particle takes through a conservative vector field, if I compute its integral, as we were doing with line integrals in the last section, if I compute that integral, all it cares about is the endpoints. And this is actually a generalization of the fundamental theorem of calculus. And I'll show you why really quick here. So this is the higher dimensional fundamental theorem of calculus. It says that the integral from a to b of a vector field, if it's conservative, d gamma, where gamma starts and ends at the points a and b, equals evaluated at the starting point or at the ending point minus the potential evaluated at the starting point. And so that's very clear, right? Because fundamental theorem of calculus wise, what does this reduce to? If that's the gradient of a potential dot gamma, that's actually just the integral of d of f of gamma. And so there it's very clear how this generalizes from the fundamental theorem. So the integral of the derivative is equal to the antiderivative evaluated at the endpoints and subtracted from each other. So that's what's really nice about these conservative vector fields. Okay, you can read that if you want to, but that's all I have. Thank you very much.